Right now, a patch of ocean south of Greenland is getting colder while the rest of the planet heats up. Scientists gave it a name, the cold blob, and it may be the first clue that the entire Atlantic Ocean is switching gears. Every 60 to 80 years, the Atlantic swings between a warm mood and a cool one. That swing decides how many hurricanes slam America. It decides whether the Midwest gets rain or drought. It even decides which fish end up on your dinner plate. Follow me down into that cold water, past a giant ocean current that is quietly slowing, all the way to a warning that could reshape the American coast forever. If this makes you see the ocean in a new way, hit like and subscribe. The Atlantic is changing. Let's find out what that means for you. Picture the Atlantic Ocean taking one slow, deep breath. That breath lasts about 70 years. The whole ocean warms for a few decades, then cools for a few decades, then warms again. This slow swing is a real cycle, and it has been going on for as long as we have kept records. One full beat, warm to cool and back to warm, can stretch across 60 to 80 years. That is longer than most people are alive. You will never feel this breath at the beach. The change in the water is tiny, only about 1 degree Fahrenheit from the warm years to the cool years. 1 degree sounds like nothing. You would never notice it in a swimming pool. But the Atlantic is enormous. It holds so much water that your brain cannot really picture it. When you warm or cool that much water by even 1 degree, you move a mountain of heat into the sky. That heat is fuel for weather. It feeds storms. It shifts where rain falls. It nudges the winds that ride across North America. So this quiet, invisible breath ends up steering things you care about. How strong the hurricane season gets. Whether farmers in the middle of the country see rain or dust. Even the price you pay for a burger. The cycle is sneaky for one reason. It hides underneath everything else. On any given day, the weather bounces around. Cold fronts, heat waves, thunderstorms, all of it. Those changes are loud and fast, so they grab all our attention. The ocean cycle works the other way. It is slow and silent, moving across whole decades. Most people go their entire lives without ever hearing about it. Think of it like the mood of a person you live with. Some days they are cheerful, some days grumpy, and that is just normal daily noise. But underneath, a person can be going through a long, slow season of life, a stretch of years that colours everything. The Atlantic has moods like that. Warm decades and cool decades. And right now, scientists think the ocean may be sliding out of one long mood and into another. That matters more than it sounds. When the Atlantic sits in a warm mood, America tends to get pounded by more hurricanes, and the farm belt in the middle of the country tends to dry out. When the Atlantic swings cool, the storms often calm down, and rain patterns rearrange across the whole country. Fish move, crops change, coastlines feel it. For the last 30 years or so, we have been living inside one of these long moods, a warm one. If you are a teenager watching this, you have never known anything else. The warm Atlantic is the only ocean you have ever lived under. It shaped the storms on the news for your entire childhood. Now the ocean may be about to flip the script. A patch of water in the far North Atlantic has started doing something it has not done in a very long time. It is getting cold. Cold enough to make serious scientists sit up and argue with each other. Before we can understand why one cold patch is such a huge deal, we have to answer a simpler question first. How did anyone ever notice a heartbeat that takes 70 years to beat? For more than 150 years, sailors have been dropping buckets into the sea. They hauled up seawater, dunked in a thermometer, and scribbled the number in the ship's logbook. Merchant ships, navy ships, fishing boats crossing the grey Atlantic. None of these sailors were trying to discover a secret climate cycle. They just wanted to know how warm the water was that day. Millions of these little measurements piled up year after year, ship after ship, spread across the whole ocean. For a long time, all those numbers just sat in dusty records. A thermometer reading from a fishing boat in the year 1880 meant nothing on its own. It was one drop in an ocean of drops. Then, around the year 2000, scientists gathered every measurement they could find. old bucket readings, modern sensors on ship engines, floating robots called buoys, and satellites staring down from space reading the temperature of the sea surface from hundreds of miles up. They stitched more than a century of data into one giant chart. And a shape appeared. It was a long, slow wave. The Atlantic ran warm in the early 1900s. It cooled down around the middle of the century, through the 1960s and 70s. Then it warmed back up near the end of the century. Up, then down, then up. A smooth rhythm that had been hiding in plain sight the entire time, buried inside all those forgotten logbooks. Imagine listening to your favourite song 1,000 times, then one day noticing a deep bass line running under everything, a part you had never heard before. That is what the scientists found. A slow beat under the noise of daily weather. Once they could see the wave, they could name it. And they could do something even better. They could figure out exactly where America was sitting on that wave right now. Naming it was harder than you would think. The ocean is messy. Every year has its own random swings from storms and winds. To find the slow cycle, scientists had to carefully strip away the fast noise and the steady climb from global warming. Underneath all of that, the wave stood out clean and clear. The discovery changed how people saw the ocean. The Atlantic was no longer just a giant tub of water sloshing around. It had a pulse, a rhythm you could track, chart, and maybe even predict. If you knew where you were on the wave, you might know what kind of decade was coming. There was one catch that made everyone nervous. The wave is slow, painfully slow. A full cycle takes longer than most careers, longer than most marriages, sometimes longer than a whole human life. That means no single scientist ever gets to watch more than 1 or 2 full swings. You're always trying to read a story when you can only see a page or 2 of it. Still, the chart was clear enough to answer the big question. As the year 2000 arrived, the wave was climbing. The Atlantic had crossed into a warm mood a few years earlier, and it was still rising toward a peak. America had just sailed onto the warm crest of the wave. And a warm Atlantic, as we are about to see, is a loaded weapon. The Atlantic has been running a fever since about the year 1995. That is the moment the wave crossed the line, when the ocean tipped from its cool mood into a warm one, and it has stayed warm ever since. 30 years and counting. For anyone under the age of 30, that warm ocean is simply the world. It is the only Atlantic you have ever known. Think about what that means. Every hurricane season you have ever watched on the news happened during this warm stretch. Every summer heat story. Every giant storm with a name that got retired because it was so deadly. All of it unfolded while the Atlantic was riding high on the warm crest of its slow wave. A warm mood does not mean the water is boiling. Remember, the difference between the warm years and the cool years is only about 1 degree Fahrenheit. You could swim in it and never feel the change, but that 1 degree spread across an ocean the size of the Atlantic adds up to a staggering amount of extra heat sitting at the surface, ready to be handed off to the sky, and the sky takes it. Warm water feeds the air above it with heat and moisture. That warm, wet air is the raw material for storms, so a warm Atlantic is like leaving the gas burner turned up under a pot. Everything that happens above the water gets a little more energy, a little more punch. During this warm stretch, the tropical part of the Atlantic, the belt of ocean near the equator where hurricanes are born, stayed unusually toasty. Warmer water in the nursery means more storms getting born, and more of them growing into giants. Scientists have watched season after season of busy, dangerous years line up neatly with this warm mood. It is a strange thing to realise. A cycle that most people have never heard of has been quietly shaping the biggest weather headlines of your whole life. When you saw flooded streets and shredded rooftops on television, you were watching the warm Atlantic flex its muscles. The warm mood does more than build storms, though. It reaches deep into the country, far from any coastline, and messes with rainfall in places you would never expect. It can turn green farmland brown. We will get to that. For now, hold on to one simple picture. For 3 decades, America has lived on the warm crest of a giant ocean wave. That crest fed the storms, warmed the summers, and set the background music for an entire generation. But waves do not stay at their peak forever. A crest, by its very nature, is the top, and the only direction left from the top is down. That is what makes this moment so tense. Scientists are staring at the wave right now and asking a simple, scary question. Have we finally reached the peak? Is the warm crest starting to roll over into the long slide down toward a cool? If it is, the change will show up first in the place a warm Atlantic hits hardest. The one kind of storm that feeds directly on all that extra ocean heat. The storm that empties American coastlines every single year. To understand what a flip would change, we first have to understand what a warm ocean built. And it built monsters. A hurricane is a heat engine, and warm ocean water is its gasoline. Strip away all the fear and the giant spinning clouds, and that is what a hurricane really is. A machine that turns ocean heat into wind. It sucks warm, wet air up off the sea surface, spins it, and flings it outward at terrifying speed. The warmer the water underneath, the more fuel the machine gets, and a hungry hurricane is a growing hurricane. Here is the rule of thumb. A hurricane needs ocean water that is at least around 80 degrees Fahrenheit to really get going. Cooler than that, and the engine sputters and dies. Warmer than that, and it roars. So when the Atlantic is riding its warm crest, the tropical waters where storms are born stay well above that magic line for longer stretches of the year. The nursery is warmer, the engine has more gas. That is why the warm mood we have lived in matched up with so many brutal hurricane seasons. When you count them up, the warm decades of the Atlantic cycle produced close to twice as many major hurricanes as the cool decades did. Twice as many of the biggest, most destructive storms. That is the difference the warm ocean makes. And these storms are almost impossible to imagine at full size. A large hurricane can spread its clouds across 500 miles of ocean, wide enough to cover several states at once. The tallest thunderclouds inside it can punch nearly 10 miles up into the sky, higher than a jet flies. In a single day, one big hurricane can release more energy than the entire United States uses in electricity in a whole year. All of that power pulled straight out of the warm seawater. The Gulf Coast has felt this again and again. Warm water in the Gulf of Mexico acts like a turbo boost. Storms that wander in over that bath water can explode in strength in just a day or two, turning from a moderate storm into a coastline flattening monster almost overnight. People go to bed watching an ordinary storm and wake up to an emergency. The year 2005 is the one everyone remembers. That season, the warm Atlantic served up a run of savage storms, and one of them drowned an American city. It was a brutal lesson in what warm water can do when it hands its heat to the sky. So for 30 years, the warm ocean loaded the dice. It did not cause every storm, and a warm sea alone does not guarantee a bad year. Winds high in the sky can still rip a storm apart, but the warm mood tilted the odds, season after season, toward more storms and stronger ones. It kept the gas tank full. Now flip the idea around. If the Atlantic really is sliding into a cool mood, that tropical nursery starts to cool. The water drops back toward and below that magic line. The engine loses fuel. The dice get loaded the other way, toward fewer and weaker storms. That would be enormous news for every family living within reach of the coast. We will follow exactly what a calmer hurricane era could mean for them. But the warm ocean did not only build storms at sea, it reached 1,000 miles inland into dry farm country and left a very different kind of scar. Far from any beach, in the dry heart of America, the warm Atlantic left its fingerprints in the dust. You would think an ocean cycle would only matter near the water. It does not work that way. The heat sitting on the Atlantic changes the giant rivers of air that flow across the whole planet. It nudges where the rain clouds go and where they skip right over, and when the North Atlantic runs warm, one of the places it tends to dry out is the middle of the United States, the farm belt, the land that grows the country's food. The way it works is like rerouting traffic. Picture the storms that carry rain into the country as cars on a highway. Warm ocean water in the North Atlantic can shift that highway, sending the rain cars on a detour around the Central Plains instead of through them. Fewer rain clouds arrive, the soil dries, the crops thirst. The most famous example is burned into American history. In the 1930s, the Great Plains dried out so badly that the topsoil turned to powder and blew away in enormous black clouds. People called it the Dust Bowl. Walls of dust rose thousands of feet into the air and rolled across whole towns, swallowing houses and burying farms. Families packed up and fled by the hundreds of thousands. And that terrible drought lined up with a warm mood in the Atlantic. It happened again in the 1950s, another stretch of severe drought across the plains, again while the Atlantic was warm. The pattern kept showing up. Warm ocean, dry heartland. The link is not perfect, and the Atlantic is only one of many things that decide whether it rains. But across the long record, the fingerprint is there. When the North Atlantic warms, the American breadbasket leans toward drought. Think about how strange that is. A patch of warm water sitting off the coast of Europe can help decide whether a corn farmer in Nebraska has a good year or watches his fields crack and curl. The ocean and the cornfield are more than 4,000 miles apart, about the same distance as flying from New York to Los Angeles and halfway back again, and yet they are tied together by the invisible rivers of air overhead. That connection cuts both ways, and this is the part that gets interesting. If the warm Atlantic helped dry out the farm belt, then a cooling Atlantic might do the opposite. It might steer those rain clouds back over the central plains. More rain, right where the food grows. For a country that feeds much of the world, that would be a very big deal. So the stakes of this ocean flip are stacking up fast. A cooler Atlantic could mean calmer hurricane seasons on the coast and wetter fields in the heartland. Two gifts at once, from the same slow swing of the sea. For 30 years, though, the warm mood held firm. The storms kept coming. The plains kept battling drought. The wave stayed near its crest, steady and strong. And then, quietly, in one corner of the ocean far to the north, something started to go wrong with the pattern. A small patch of sea began to misbehave. It began to cool while the rest of the world kept heating up. That patch would soon have a nickname, and it would put every scientist watching the Atlantic on high alert. South of Greenland, a patch of ocean started turning the wrong colour. For years, scientists have made maps of how the world's oceans are heating up. On these maps, warming water glows red and orange, and almost the entire globe is painted in those hot colours now. The planet is running a fever, and the maps show it clearly. But on every one of these maps, in the North Atlantic, just below Greenland and Iceland, there is a strange blue splotch, a cold spot, a place that stubbornly refuses to warm up while everything around it does. Scientists gave it a blunt, perfect nickname, the cold blob. The cold blob is not small. It sprawls across a chunk of ocean larger than the state of Texas, a giant patch of sea that has cooled off over the past decade or so while the rest of the planet has baked. Sitting there on the map, a cold blue island in a sea of red, it looks completely out of place. It looks wrong. It started grabbing attention around the middle of the 2010s. A run of brutally harsh winters battered the North Atlantic, with fierce winds dragging heat out of the water like an open freezer door left swinging. Season after season, those winters chilled the sea and pushed the cold down into the depths where it settled and stayed. The blob outlasted every spring. It stayed put year after year, glowing a stubborn blue while the map all around it turned a deeper red. Scientists gave it a second nickname. They call it the warming hole. The whole planet is heating up, painting the map hot from pole to pole, and yet here sits one gaping hole in that pattern, one place the heat skips. A hole in global warming punched into the sea below Greenland. At first, plenty of scientists shrugged it off. The ocean is huge and lumpy. There are always warm patches and cold patches drifting around. A single cool splotch, even a big one, might just be a temporary mood, here for a few winters and gone by the next. Nothing to lose sleep over, but the blob would not leave. It dug in and stayed, growing more stubborn by the year, and a cold patch that refuses to fade starts to look less like random noise and more like a message. The question was what, exactly, it was trying to tell us. There are two possible messages, and they could not be more different. This is the fork in the road that the whole story hangs on. The first possibility is almost cheerful. Maybe the cold blob is the leading edge of that natural ocean cycle, finally swinging back to its cool mood. The far north always cools first when the wave rolls over. If that is what this is, then the blob is simply the Atlantic doing its normal thing, and America might be in for calmer storms and wetter farms. The second possibility is far darker. Maybe the cold blob is a warning sign of something breaking in the deep ocean, something that has kept the whole North Atlantic warm and livable for thousands of years. If that is what this is, the story stops being about a friendly cycle and becomes something much scarier. For now, hold the hopeful idea in your head, the cold blob as a natural cool phase beginning. To take that idea seriously, scientists needed to measure just how cold the blob had gotten. When they did, the number they found stopped them in their tracks. When scientists finally measured just how cold the blob had become, the reading stopped them cold. The water in that patch south of Greenland had plunged far past a mild chill. It had dropped all the way down to temperatures the region had not seen in about 30 years. To find water that chilly there, you would have to go back to the 1990s, and the 1990s, remember, was the tail end of the last time the Atlantic sat in its cool mood, right before it flipped warm. That is the detail that made everyone lean in. The cold blob was now as cold as the ocean had been during the previous cool phase. It matched. It was as if the far North Atlantic had reached back 3 decades and grabbed a temperature straight out of its own cool era. For scientists tracking the slow wave, this looked like a clue with a capital C. The cool mood always begins in the far north, in exactly this stretch of sea. The subpolar region, the ring of ocean below Greenland and Iceland, is the spot that cools first when the wave rolls over from warm toward cool, so a deep chill showing up right there at the exact strength of the last cool phase is precisely what you would expect if the Atlantic were starting to flip. Picture a pot of water you have had on the stove for 30 years. Suddenly one corner of it goes cold and not lukewarm, but as cold as it was the last time you turned off the burner. You would start to wonder if the flame underneath had changed. That is the wondering scientists are doing right now with the North Atlantic. The timing made it even more striking. The warm mood had been running for around 30 years by this point, which is right in the range where these warm stretches tend to run out of steam. Warm phases do not last forever. They peak, they hold, and then they roll over. The wave had been climbing and cresting for 3 decades, and now the coldest corner of the ocean had plunged to a cool phase reading. The clock and the thermometer seem to agree. None of this proves the flip is happening. A single cold patch, even a deep and stubborn one, is one piece of a giant puzzle. The ocean could warm that spot right back up in a few years and make everyone forget the whole thing. Scientists are careful people, and they hate jumping to conclusions from one dramatic reading. But the readings kept coming, and they kept pointing the same direction. The blob stayed cold, it stayed big, and it stayed sitting in the one place that matters most for the start of a cool mood. So the evidence was piling up on one side of the scale. A warm phase running long in the tooth. A cold patch as chilly as the last cool era. A location that fits the pattern perfectly. Put it all together, and a bold idea starts to feel less crazy and more possible. Some scientists looked at all of this and said the quiet part out loud. The Atlantic, they argued, might be flipping its mood right now, right in front of us. It was a big claim, and not everyone was ready to believe it. Some scientists now say the Atlantic is changing its mood right in front of our eyes. This is the bold claim, the one that turns a quiet patch of cold water into a story worth telling. After 30 years of a warm ocean, a group of researchers looked at the cold blob, looked at the aging warm phase and made a call. They said the wave has crested. The warm era is ending. The long slide toward a cool Atlantic has begun. They even put numbers on it. A few years back, one study crunched the ocean data and gave the flip a real chance of happening soon. Their estimate landed around 7 in 10. In other words, they judged it more likely than not that the Atlantic would tip into its cool mood within just a few years. 7 in 10 is a careful, calculated call. It is a coin that lands cool more often than warm. If that call is right, it is a huge deal. It would mean the background music of American weather is about to change for the first time in a generation. The storms, the droughts, the rainfall maps, all of it would slowly begin to shift toward the patterns of a cool Atlantic. The world you grew up in would start to fade, and a different one would take its place. But you have to hold this claim carefully, like a hot pan. It is a forecast, an educated prediction about a slow and stubborn ocean, and forecasts about this cycle are hard. Very hard. Remember, the wave takes 60 to 80 years to complete one swing. Scientists have only had good, detailed ocean data for a few decades. Trying to spot the exact moment of a flip using just a few years of readings is like trying to guess the ending of a movie you walked into halfway through. That is why plenty of other scientists are not sold. They look at the same ocean and urge patience. Cold patches have come and gone before, they point out, without the whole cycle flipping. The blob could be a false alarm, a few chilly years that fade away and leave the warm mood chugging along. History is full of moments that looked like a turning point and turned out to be nothing. So you have a genuine split. One camp sees the cold blob and says the flip is here, or nearly here. Another camp sees the same blob and says slow down, we've been fooled before, wait for more evidence. Both sides are looking at the exact same ocean. They just read the story differently. This is how science actually works, out on the frontier where the answers are not in yet. Smart people stare at the same clues and argue hard about what they mean. The arguing is the engine that grinds slowly toward the truth. And this particular argument has real weight, because the two sides are fighting over far more than a label. They are debating your future. Whether the coast gets a break from storms, whether the farm belt gets its rain, whether the whole rhythm of American weather is about to turn a corner. There is one more twist that makes the fight even sharper. When scientists look closely at the cold blob, it does not quite behave the way a clean, simple flip should. And that oddness is where the argument gets truly heated. When the Atlantic changes its mood, it does not ease into it gently. You might expect a cycle this slow to shift like a sunrise, creeping from one state to the next over many long, quiet years. Sometimes it does. But the record shows that the Atlantic can also turn with surprising speed once it makes up its mind. The wave can roll over faster than almost anything else in the climate. Look back at the last big flip. In the middle of the 20th century, the Atlantic slid from warm into cool, and it did it at a real clip. The ocean surface dropped in temperature decade after decade, cooling at a pace that outran the slow, steady creep of global warming. In fact, that cooling ran roughly twice as fast as the background warming of the planet was climbing at the time. The cycle can move quickly enough to overpower the slow drift of a heating world, at least for a while in one region. That speed is the whole reason this matters to you right now, and not to some distant future generation. If the Atlantic really is flipping, the change would not take 100 years to arrive. It could reshape the pattern of American weather within a decade or two. That is soon enough that a teenager watching this could live through the entire shift, from warm world to cool world, before they hit middle age. Why can something so massive turn so fast? Picture a heavy revolving door, the kind in a big hotel lobby. When it is standing still, it feels impossible to budge. You lean and push, and nothing happens. But once it finally starts to swing, all that weight becomes momentum, and suddenly the door is moving fast and pulling you with it. The Atlantic cycle has that same feel. It resists change, holding one mood for decades, and then it commits, swinging hard and carrying the whole ocean with it. Underneath the surface, the reason is tied to how the ocean moves its heat around. Warm and cold water are always on the move. They travel in slow, looping currents, carrying heat north and south. When those currents shift their strength, they can flip a whole region from warm to cool relatively quickly, because they are moving heat by the ocean load. Change the delivery of heat, and the temperature of the sea surface follows. So the flip, if it is truly underway, could be one of the faster changes in nature that you will ever get to witness. Slow by the standards of a thunderstorm, lightning quick by the standards of the deep ocean. That should make you sit up. A change this big, arriving this fast, aimed straight at the country you live in. But here is the wrinkle that keeps scientists up at night. A clean, normal flip has a certain look to it. The whole North Atlantic should cool together top to bottom, like a single sheet of water sliding from warm to cool. That is the textbook version. The cold blob is not following the textbook. When scientists map out the temperatures across the whole Atlantic, they see something lopsided and strange, a pattern that does not match a simple, healthy flip at all. And that mismatch is exactly what splits the room. It is where the shouting really starts. Now the scientists start shouting at each other, and the cold blob is the reason. A clean, ordinary flip of the Atlantic cycle should look tidy. The whole North Atlantic ought to cool off together, the far north and the tropics sliding into a cool mood as one. That is the simple picture, the one that has shown up in past cool phases. That is not what the map shows today. When scientists chart the temperatures across the Atlantic right now, they see a lopsided, patchy mess. Up in the far north, below Greenland, the cold blob is deeply chilled, exactly where a cool phase should begin. But drop down toward the middle of the ocean, into the warmer subtropical waters, and something odd appears. That region is running hot, unusually warm. And down near the equator, the tropical belt shows its own patchy mix of cool spots. So instead of one big, even cooling, the Atlantic looks like a patchwork quilt. Cold in the north, warm in the middle, spotty in the tropics. It is a strange, mixed-up pattern, and it does not fit the clean textbook flip that everyone learned about. That single fact is what splits the room of scientists in two. One camp looks at the deeply cold north and says the flip has clearly begun. The far north is where a cool phase always starts, they argue, so the rest of the ocean will follow in time. Give it a few years, and the cooling will spread south until the whole pattern falls into place. The blob to them is the opening act. The other camp points straight at that warm middle and says not so fast. If you measure the mood of the whole Atlantic by averaging it all together, the warm subtropical water can cancel out the cold northern blob. Do the math across the entire ocean, and by some measures the Atlantic still reads as warm overall even today. The storm forecasters who plan for hurricane season have leaned this way, treating the ocean as still sitting in its warm mood for now. So you can look at the same exact ocean and reach two opposite conclusions. Cold north says cool phase is coming, warm middle says warm phase is hanging on. Both camps are staring at the identical map, they just weigh the pieces differently. This argument reaches far past labels and definitions. It is a fight about which future is on the way. If the north wins and the cooling spreads, America gets the cool phase, with all its calmer storms and shifting rains. If the warm middle holds on, the old pattern grinds forward, and the busy hurricane seasons keep coming. There is a deeper reason the patchiness worries the careful scientists, and it is the shadow hanging over this whole story. A normal cool phase cools the north and warms nothing strange, but a lopsided pattern with an oddly cold north sitting next to unusual warmth can be a sign that something else is going on down in the deep ocean. Something bigger than the friendly cycle. We will follow that darker clue soon, all the way to the ocean floor. But first, let us assume the hopeful camp is right. Let us say the cool phase truly is arriving. If it is, the payoff for America is enormous, and it starts with the storms that empty our coastlines every year. If the Atlantic really is cooling, the first gift could be a much quieter hurricane season. Remember how the whole storm machine works. A hurricane runs on warm ocean water, and it needs that water to sit around 80 degrees Fahrenheit to grow into a monster. A warm Atlantic keeps the tropical nursery above that line for long stretches, feeding the engine. A cooling Atlantic does the reverse. It drops the temperature of that nursery back down, pulling fuel away from the storms before they can build. The history is striking. When scientists compare the warm decades of the cycle to the cool decades, the warm ones produced close to twice as many major hurricanes, twice as many of the giant coastline flattening storms. Flip the ocean to cool and that number tends to fall. Fewer big storms form, and the ones that do form have a harder time growing to full strength. For the tens of millions of Americans living within reach of the Gulf and East Coasts, that would be an enormous relief. Picture a stretch of years where the tropics stay quieter, where fewer storms spin up in the first place, where the ones that do arrive run out of fuel before they can explode into something catastrophic. That is the kind of break a cool Atlantic can hand to a coastline. It would change the rhythm of an entire region. Right now, every summer along the southern coast comes with a low, constant hum of worry. Families track the tropics on their phones, they stock up on water and plywood, they keep an evacuation plan in the back of their minds from June clear through November. A calmer Atlantic could soften that dread, turning the worst seasons into merely ordinary ones. Now do not oversell it. A cool ocean does not switch off hurricanes. Storms will still form. Bad years will still happen. Even in a cool phase, all it takes is one storm hitting one city in the wrong spot to cause a disaster. The cool Atlantic does not build a wall around the coast. It just loads the dice back toward fewer and weaker storms, the same way the warm phase loaded them toward more and stronger ones. And there is a hard truth riding underneath all of this. Even as the ocean cycle might calm the storms, the wider warming of the planet is pushing the other way. A hotter world can make individual storms wetter and more intense, dumping heavier rain and pushing higher water inland. So a cool phase might mean fewer storms, while each one that does land could still pack a serious punch. The two forces wrestle each other. Still, if you had to choose, fewer storms is a gift worth having. A quieter tropical Atlantic would ripple out into daily life in ways most people never think about. It would touch how cities plan, how coasts rebuild, and it would reach straight into something that hits every coastal family right in the wallet, whether a storm ever shows up at their door or not. Because there is a second storm that follows every hurricane. It does not have wind or rain. It arrives weeks later in the mail, and it can hurt a family for years. That storm is made of money, and a cooling Atlantic could change it in a big way. Every hurricane leaves behind a second storm, and this one is made entirely of bills. When a major hurricane slams into an American coast, the damage can be staggering. A single big storm can cost more than $100 billion in wreckage. That is a number so large it slides right off your brain. So try this. Imagine stacking up the cost of the most expensive storms, and each one alone could pay for building dozens of large hospitals or thousands of new schools, all wiped out in a single weekend of wind and water. Someone has to cover that cost, and a big piece of it lands on insurance. Insurance is the deal where you pay a company a little bit every month, and in return they promise to help pay for the damage if disaster strikes your home. It works fine when disasters are rare. It gets shaky when disasters come again and again. That is exactly what 30 years of a warm, stormy Atlantic has done. As the big storms kept battering the coast, the insurance companies kept paying out fortunes, and then they did the obvious thing. They raised their prices. In the most storm-exposed corners of the country, the monthly cost of protecting a home has climbed painfully high. Some companies have gotten so nervous about hurricanes that they stopped selling coverage in certain coastal areas altogether, leaving families scrambling for any protection they can find. So here is where a cooling Atlantic could quietly change millions of lives. If the ocean flips cool and the big storms grow rarer, the insurance companies face fewer giant payouts. Over time, that could ease the pressure on prices. Coverage might become easier to find. The monthly bill that has been crushing coastal families could stop climbing so fast and maybe even settle back down. Money that vanished into insurance could go toward groceries or savings or a normal life. It reaches beyond private homes too. When storms are rare, the government does not have to drain its emergency funds year after year to rebuild flooded towns and shattered roads. Those funds stretch further. A dollar saved on disaster is a dollar that can go somewhere else. A calmer Atlantic could ripple through entire budgets, from a single family kitchen all the way up to the national treasury. But keep your feet on the ground here. Insurance companies are slow to lower prices, even when the risk drops. They got burned by 30 years of storms, and they will want to be sure the calm is real before they hand back any savings. Do not expect your bill to fall the moment the ocean cools. And the bigger warning still stands. Even if hurricanes ease, the warming planet keeps pushing the sea higher, inch by inch, all along the coast. Higher seas mean worse flooding from any storm that does arrive, and even from ordinary high tides. So the money storm never fully clears. It just changes shape. Still, the possibility is real. A shift in a distant patch of ocean could loosen the financial grip on an entire coastline. That is the strange power of this cycle. It reaches from the deep sea straight into your family's bank account. And the good news does not stop at the water's edge. Follow the cooling Atlantic inland, and it could touch something even more basic than money. It could touch the food on America's table. A cooler Atlantic could turn the dry heart of America green again. Go back to that strange connection from before. When the North Atlantic runs warm, it tends to steer rain away from the middle of the country, leaving the farm belt to bake and crack. That link is one of the reasons the warm decades lined up with brutal droughts on the Great Plains. So if the ocean flips cool, the logic runs the other way. The cool Atlantic could nudge those rain clouds back over the heartland, right where the food grows. That would be an enormous deal because of what the American heartland actually is. This stretch of land in the middle of the country is one of the greatest food factories the world has ever seen. It grows a staggering share of the planet's corn and soybeans. The United States alone produces roughly a third of all the corn on Earth. Much of it comes from this one broad belt of black soil, feeding Americans and people in dozens of countries around the globe. For crops like these, rain is everything, and timing is everything. There is a stretch in late spring and early summer, when the young plants are growing fast, where a good soaking of rain can make the whole season. Get the rain then, and the fields turn a deep, endless green, and the harvest comes in heavy. Miss it, and the plants wilt and the yields collapse. A cooling Atlantic that delivers steady rain during those key weeks could mean bumper harvests, full-grain silos, and steadier food prices at the store. Steadier food prices touch every single person, even those who have never set foot on a farm. When harvests are strong, the cost of everything built on corn and grain stays gentle. That includes bread, cereal, cooking oil, and the feed that fattens cattle and chickens. It reaches all the way to the price of a burger and a glass of milk. A wet, healthy farm belt is quietly good news for your kitchen. But nature rarely hands out a gift without a catch, and here is this one. More rain is only a blessing up to a point. Push past that point, and helpful rain becomes destructive flooding. Fields can drown, seeds can rot in soggy ground before they ever sprout, and there is an extra danger lurking in the warming climate. Warmer air holds more moisture, so when it does rain now, it can dump the water in violent, sudden bursts instead of gentle soaks. A cool Atlantic bringing more rain, in a warmer world that dumps it all at once, could swing from drought straight into flood. So the cool phase does not promise a perfect harvest every year. It shifts the odds toward more rain in the heartland, which is mostly a good thing for a hungry world, as long as the rain arrives kindly, and not all in one furious afternoon. Line it all up, and the cool Atlantic starts to look like a generous friend to America. Calmer storms on the coast, lighter insurance pressure, wetter, greener farm country, 3 gifts, all from one slow swing of the sea. But every gift the cool Atlantic hands to America, it seems to take away from somewhere else on Earth. And in one part of the world, the last cool phase did not bring relief. It brought catastrophe. The last time the Atlantic went cool, a slow disaster unfolded an ocean away. The same ocean swing that could green the American farm belt does the opposite thing thousands of miles to the east, in a band of Africa called the Sahel. The Sahel is a wide strip of dry grassland that runs across the continent, sitting just below the Great Sahara Desert. It is a land that lives and dies by a single short rainy season each year. The people there farm and herd animals, and everything depends on those rains arriving on time. The trouble is that the Atlantic helps decide whether those rains come at all. When the ocean is warm, it tends to pull moisture toward the Sahel, and the rains are more generous. When the Atlantic swings cool, that flow of moisture weakens, and the rains can fail. The land dries, the crops die, the animals starve, and then the people do too. This already happened, and it was one of the great tragedies of the last century. Through the 1970s and into the 1980s, while the Atlantic sat in its cool mood, the Sahel plunged into a horrific grinding drought that lasted years. The rains simply stopped coming. Crops withered across an entire region. A famine spread, and it killed staggering numbers of people. Hundreds of thousands of lives were lost to hunger and its miseries. Whole villages emptied as families walked for days searching for food and water that were not there. That famine seared itself into the world's memory. It was one of the first times a global audience watched a mass starvation unfold on their television screens, and it helped spark some of the biggest relief efforts the world had ever seen. And underneath that human catastrophe, quietly steering the whole thing, was the cool mood of the Atlantic Ocean, choking off the rains. So here is the heavy truth of this ocean flip. The very same cooling that could calm America's storms and water its crops could, at the same moment, help dry out the Sahel and threaten millions of the most vulnerable people on the planet with hunger. One swing of the sea. Two completely opposite fates depending on where you happen to live. It is a brutal reminder that the climate does not care about borders. A change in a patch of water near Greenland reaches out and touches a farmer in Nebraska and a herder in Africa in the same season, handing one of them rain and the other one dust. The ocean plays no favourites. It simply moves its heat and its moisture, and the human consequences fall where they fall. This darker side of the cool phase is exactly why scientists do not treat any of this as simple good news. A cooling Atlantic is a mixed bag for the world, a gift in some places and a threat in others. And the places most likely to suffer are often the ones least able to defend themselves against a failed harvest. For now, though, keep your eyes on America and follow the cooling ocean back home. Because the cool Atlantic would not only change the rain and the storms, it would quietly reshape life beneath the waves, right off the American coast, and change something that ends up on your dinner plate. Beneath the cooling Atlantic, the fish begin to move. Fish do not read the news or check a thermometer, but they feel water temperature in their bones, and it rules their lives. Most fish are picky about how warm or cold their water is. Each kind has a comfort zone, a band of temperature where it can feed and breed and thrive. Push the water outside that zone, and the fish do the only thing they can. They pack up and swim to find water that feels right. For years now, as the ocean has warmed, fish along the American coast have been drifting steadily northward and into deeper, cooler water, chasing their comfort zone as it slides toward the poles. In some places, populations of fish have shifted tens of miles north over just a few decades. Entire fisheries have been slowly moving up the map following the cold. A cooling Atlantic could throw that whole migration into reverse or scramble it in ways that are hard to predict. Think about the famous catches of the North Atlantic. Cod, the fish that built entire coastal towns in New England. Lobster, the prize of the Maine coast. Mackerel and herring, the silvery schools that feed everything above them. Every one of these responds to temperature. Shift the water, and you shift where they live, how many there are, and who gets to catch them. That matters far beyond the fish themselves. Along the American coast, whole towns have been built around a single catch. Their harbours, their jobs, their restaurants, their entire way of life depend on a certain fish showing up in certain waters year after year. When the fish move, the money moves with them. A town that has hauled in lobster for 100 years can suddenly find its waters too warm or too cold, while a town farther up the coast lands a catch it never had before. Fortunes shift with the temperature of the sea. It reaches your plate too, even if you live 1,000 miles from any ocean. When a fish becomes harder to catch, it gets more expensive at the market. When a species thrives and floods the docks, its price drops. So the slow swing of the Atlantic quietly helps decide whether that fish sandwich or that seafood dinner is a cheap treat or a pricey splurge. The ocean cycle reaches right into the seafood aisle of your grocery store. Here is the tricky part, though. A cooling ocean cycle is now wrestling with the steady warming of the whole planet, and the fish are caught in the middle of that tug of war. The cool phase might pull some species back south, while the long-term warming keeps nudging them north. The result could be a messy, confusing reshuffle, with fish populations jumping around as the two forces fight over the thermostat. Fishermen may face years of surprises, never quite sure what their nets will bring up. One thing is certain, the map of American fishing is not fixed. It moves with the sea, and a flip in the Atlantic would redraw it once again. So the cooling ocean touches the storms, the farms, and now the fish. It is reaching into every corner of American life, and it is about to reach one more place, a threat that has terrorized whole states in recent summers, turning the sky orange and the air unbreathable. A wetter, cooler east could take some of the heat off a nation that keeps catching fire. In recent years, drought has gripped enormous stretches of the United States. At times, more than half of the lower 48 states have been locked in some level of drought at once. Picture that. You could draw a line across the country and find dry, thirsty land on both sides of it. Parched soil, low rivers, dying crops, and forests turned into tinder just waiting for a spark. That dryness feeds one of the most terrifying threats of the modern American summer: wildfire. When the land dries out, every forest and grassland becomes fuel. A single lightning strike, a stray spark, a downed power line, and a fire can erupt and race across the landscape faster than a person can run. In the worst years, walls of flame have swallowed whole towns, filled the sky with choking smoke for weeks, and forced hundreds of thousands of people to flee their homes. This is where a cooling Atlantic could lend a hand, at least in one part of the country. Remember, a cool phase tends to steer more rain into the central and eastern United States. More rain means damper soil, greener plants, and fuller rivers. Damp forests do not burn the way dry ones do. So if the cool Atlantic delivers steadier rainfall across the east and the middle of the country, it could ease the drought there and take some of the wildfire pressure off those regions. A wetter heartland is a heartland that is harder to set ablaze. That would be a real gift. Fewer fires means cleaner air, safer towns, and fewer families watching everything they own disappear in smoke. It means firefighters stretched a little less thin and forests given a chance to recover between bad years. But do not celebrate too early, because this gift comes wrapped in some serious limits. The worst wildfire country in America is out west, and the west is a different beast. The cool Atlantic mainly waters the eastern and central states. It does much less for the dry mountains and forests of the far west, where heat, long droughts, and other patterns rule the fire season. So the cooling ocean is no magic hose that puts out the whole country. It helps one region while leaving the most fire-prone one largely on its own. There is the other catch too, the one that keeps showing up. In a warmer world, when the rain finally comes, it can arrive in violent bursts. So a region could swing from a dangerous fire season straight into a dangerous flood season, trading one disaster for another. Damp is safer than dry when it comes to fire, but a sudden wall of water brings its own kind of ruin. Still, add it to the pile. Calmer storms, easier insurance, wetter farms, shifting fish, and now a possible break from wildfire across part of the country. Laid out like that, the cooling Atlantic can start to look like a hero riding to America's rescue. It is time to be honest about that hopeful story, because it hides a catch big enough to swallow all the good news whole. The cool Atlantic is not the rescue it appears to be. The cool Atlantic can fool you into thinking the climate problem is fixing itself. Look at everything we have stacked up. Fewer hurricanes, cheaper insurance, greener farms, a break from wildfire in the east. If you squint, it almost looks like the ocean is quietly solving climate change for us, cooling things down right when we need it. That is the trap. That is the story you must not fall for. Here is why. The cooling from the Atlantic cycle is temporary, and it is small. Remember the size of this swing. The whole difference between the warm mood and the cool mood is only about 1 degree Fahrenheit at the ocean surface. That swing can shove weather patterns around, but it does nothing to stop the steady, relentless heating of the entire planet happening underneath it. Global warming keeps climbing the whole time, year after year, no matter which mood the Atlantic is in. Think of it like walking up a long escalator that is always moving up. That escalator is global warming, carrying the whole world higher and hotter every year. The ocean cycle is just you taking a few steps backward on that escalator during the cool phase. For a while it feels like you're dropping down, getting a break from the heat. But the escalator never stops climbing. The moment the cool phase ends and the warm mood returns, you get carried right back up, now even higher than before because the escalator has been rising the entire time you were distracted. So a cool Atlantic might hand America a calmer decade or two. Then the cycle will swing back to warm, as it always does, and the storms and droughts will return, layered on top of a planet that has kept heating the whole time. The cool phase does not cancel the warming, it just briefly hides it, and hands us a bill to pay later with interest. That alone would be reason enough to keep our guard up. But there is a second darker problem, and it is the one that has serious scientists genuinely worried. It brings us all the way back to that cold blob south of Greenland, the patch of water that started this whole story. We have been telling the hopeful version. In that version, the cold blob is simply the friendly ocean cycle, rolling over into its cool mood, bringing America its mixed bag of gifts. Calm story, manageable. The kind of thing the planet has done over and over for thousands of years. But some scientists look at that same cold blob and see something else entirely. They look at how the north is oddly cold, while the middle of the ocean runs strangely warm, that lopsided pattern that broke the textbook. And they suspect the blob is not the gentle cycle at all. They fear it is the surface bruise of a much deeper wound, a sign that one of the most important systems on the entire planet is starting to break down. Because underneath the friendly cycle, hidden in the deep, there is a giant machine that has kept the North Atlantic warm and steady for longer than human history. A vast river inside the ocean. And that cold patch on the map might be the first hint that this machine is beginning to slow down. If it is, everything we just celebrated changes into something far more dangerous. There is a giant machine hidden inside the Atlantic Ocean, and it may be breaking down. We spent the whole first half of this story on the hopeful idea. The cold blob as the friendly ocean cycle, rolling into its cool mood and handing America a mixed bag of calmer storms and wetter farms. It is a comforting story. It may even be true. But it's only one of the two paths, and now we walk down the other one, the dark one, the one that keeps climate scientists awake at night. Start with a simple, strange fact. The North Atlantic should be a lot colder than it is. Look at a globe and follow the lines of latitude. London and Paris sit as far north as the icy, snowbound middle of Canada. By all rights, Western Europe should be a frozen land of long, brutal winters. Yet people there stroll through mild green cities, growing gardens where you might expect glaciers. Something is keeping that whole side of the planet warm, and that something is a river inside the sea. It is a vast current of water that flows through the Atlantic like a conveyor belt, hauling warm water up from the tropics toward the far north. This warm water carries heat, and as it travels, it slowly leaks that heat into the air above it. That leaked heat is what keeps the North Atlantic and the lands around it far warmer than they should be. The current is, in a very real way, the central heating system for a huge chunk of the planet. Now here is the part that should make your stomach drop. Remember exactly where the cold blob sits. It sits in the far North Atlantic, right in the zone where this warm current arrives and dumps most of its heat into the sky. That is the delivery spot, the final stop on the conveyor belt. So think about what a cold blob in that exact place could mean. If the current was slowing down, it would carry less warm water north. Less warm water means less heat delivered to that final stop, and less heat delivered would leave that patch of ocean cooler than the world around it. A cold patch, a blob, sitting in precisely the place where a weakening current would leave its mark. That is why some scientists look at the cold blob and do not see a friendly cycle at all. They see a fingerprint, a smudge left behind by a great ocean machine that is beginning to falter. The cool water is a symptom, and the disease is a slowing current. If they are right, this changes everything. The friendly cycle comes and goes on its own, harmless and natural, part of how the planet has always worked. A weakening of the deep current is a different beast entirely. It would mean one of the largest and most important systems on Earth is winding down, with consequences that reach far beyond a few calm hurricane seasons. To understand just how much would be at stake, you have to really understand this machine, how it works, why it moves, and what has kept it running steadily for longer than human civilization has existed. Because once you see how the conveyor belt actually turns, you will understand why a single melting island near the top of the world could be enough to jam it. Deep in the North Atlantic, near Greenland, the ocean does something that sounds impossible. It falls. To see how the great current works, follow one drop of water on its journey. Our drop starts down in the warm tropics, near the equator, sitting at the sun-baked surface of the sea. Warm water is light and buoyant, so it floats along the top. Powerful winds and the spin of the planet push this warm surface water northward, up along the eastern coast of the United States, and out across the Atlantic toward Europe. This is the warm half of the conveyor belt, a broad river of heat flowing toward the pole. As our drop travels north, two things happen to it. First, it gives away its heat to the cold air above, warming the sky and cooling itself down. Second, some of the water around it evaporates into the air, and evaporation leaves the salt behind. So our drop slowly becomes colder and saltier as it heads north. Now cold water is heavier than warm water, and salty water is heavier than fresh water. Our drop is now both cold and salty, which makes it dense and heavy, like a swimmer wearing a weighted belt. By the time it reaches the far North Atlantic near Greenland, it has become so heavy that it can no longer stay at the surface, so it sinks. It plunges straight down into the black depths of the ocean, thousands of feet below. This sinking is the secret engine of the whole system. All across the northern seas, countless tons of cold, salty water are dropping into the deep at once, creating a hidden waterfall grander than anything on land. In one spot near Iceland, water pours over an underwater cliff and falls more than 2 miles straight down, a cascade no human eye will ever see, far taller than any waterfall you could visit. Once our drop reaches the bottom, it begins the return trip. It creeps slowly southward along the ocean floor, a deep cold river running beneath the warm one above it. Eventually, far away, it rises back to the surface, warms up again, and rejoins the flow. One full loop can take 1,000 years to complete. Put it all together and you get a single connected belt. Warm water flowing north on top, sinking near Greenland, and cold water flowing south along the bottom. Around and around endlessly, moving heat across the whole planet. And the scale of it is almost beyond imagining. This current carries more water than every river on Earth combined, many times over. The flow of warm water it pushes northward is greater than 100 Amazon rivers pouring along at once. It is one of the most powerful movements of water anywhere on the planet, and it runs day and night, century after century, without ever stopping to rest. The sinking near Greenland is the heartbeat of the machine. As long as that cold, salty water keeps dropping into the deep, the belt keeps turning and the heat keeps flowing north. But notice what the sinking depends on. It needs the water up north to stay heavy, cold and salty and dense enough to plunge. Take away either the cold or the salt and the water might stop sinking, the engine would stall, and near Greenland something is happening right now that is stealing the salt away. Reach out and touch the coast of Europe, and you're feeling heat that travelled thousands of miles by sea. We already saw the strange fact. London sits as far north as the frozen heart of Canada, yet it almost never sees the brutal winters you would expect. The reason is the warm current we just followed, carrying tropical heat up and across the Atlantic and breathing it out over Europe. Scientists figure that without this flow of warm water, large parts of Europe could be many degrees colder, cold enough to change what crops can grow and how people live through the winter. Picture two cities at the very same distance from the North Pole. One gets the warm current and one does not. The city with the current enjoys green parks and gentle winters. The city without it shivers under snow and ice for months. That is roughly the gap the ocean conveyor creates. It is the difference between a mild country and a frozen one, decided entirely by a river in the sea. The United States feels the current too, in its own way. As that warm water rushes up along the east coast, it shapes the weather of the entire eastern seaboard. It feeds moisture and heat into the storms that roll up the coast. It sets the temperature of the water where hurricanes travel. The whole rhythm of life along the Atlantic coast is tied to this passing river of warmth. The most famous stretch of the current runs right past America, and you may have heard its name, the Gulf Stream. It is the warm, fast-moving part of the belt that hugs the eastern United States before peeling off across the ocean toward Europe. It is a genuine river within the sea, warmer and bluer than the water around it, moving so much water so quickly that early sailors learned to ride it like a moving walkway to cross the Atlantic faster. For as long as human beings have kept records, this current has been a fixed fact of the world. Dependable, always there. Sailors mapped it. Farmers in Europe unknowingly built their whole way of life on the warmth it delivers. Coastal cities in America grew up alongside it. Nobody ever had to wonder whether it would keep running, any more than you wonder whether the sun will rise. It simply always did. That is what makes the new evidence so unsettling. This current, this dependable giant that has warmed half the world for longer than history, is showing signs that it is slowing down. Not stopping? Not yet, but weakening, losing some of its strength, decade by decade, in a way that scientists can now measure. And a current that is slowing is a current that delivers less heat to the north, which brings us right back to that stubborn cold patch on the map. The idea that this ancient, reliable river could weaken, or one day even stall, sounds almost too big to believe. For a long time it lived only in scary movies and wild speculation. Serious scientists were careful not to cry wolf about it. But over the past few years, the measurements have started piling up. Real data, from real instruments in the real ocean, and that data is telling a story that has turned careful scientists into worried ones. Here is the first clue that changed the conversation. For decades, scientists could only guess how fast the Great Current was flowing. Now they can measure it, and the numbers are shrinking. Measuring an ocean current is harder than it sounds. You would need far more than a stick dipped in the water to read its speed. This current is thousands of feet deep and hundreds of miles wide, spread across an entire ocean. So scientists got clever. They strung lines of instruments across the Atlantic from one side to the other, dangling sensors at many depths to catch the water as it flowed past. They parked floating robots in the sea to drift and report back. They pulled together more than 100 years of temperature and saltiness records from ships and buoys. Then they used all of it to reconstruct the strength of the current, going back decade after decade. They built a picture of how fast the conveyor belt has been turning across a long stretch of time. And when they stepped back and looked at that picture, they saw a slow, steady decline. The current has weakened. Careful studies that piece together the last 70 years or so keep landing on the same uncomfortable answer. The belt is turning more slowly than it used to. The pump that drives the whole system has lost some of its push. Now, honesty matters here, because this is hard science on a moving target. The exact amount of the slowdown is still argued over. Some studies find a bigger drop, some find a smaller one, and a few scientists are not convinced there is a clear trend at all. Measuring something this huge with records that are patchy in places leaves real room for debate. Nobody should pretend the number is nailed down to the last decimal. But here is what has shifted the mood among scientists. When you gather up all the separate studies, using all the different methods, most of them point the same direction, down. Different teams, different tools, different slices of data, and yet the arrow keeps landing on a weakening current. When many roads lead to the same place, people start to believe the destination is real. Think of it like a dozen different doctors examining the same patient. One checks the heartbeat, one runs a blood test, one takes an image, one asks about symptoms. If every single one of them, using their own method, comes back saying the patient is running down, you stop dismissing it as a fluke. The agreement itself becomes the warning. That is where we are with the current. The heartbeat of the North Atlantic appears to be softening, and the evidence for it is coming from many directions at once. Still, a slowdown measured on a chart can feel abstract. Numbers on a graph do not splash cold water in your face. Scientists wanted something more direct, more physical. They wanted to reach out and touch the slowdown to find its mark written somewhere in the real ocean, and they found it in the strangest possible place. The mark was cold, and it reached deep. When they dropped their measurements down below the surface into the dark water of that cold blob, they discovered a chill that could not be explained by the weather at all. To understand why that deep cold was such a shock, you have to go down with them, thousands of feet beneath the waves. The real shock was not at the surface. It was buried thousands of feet down in the black cold of the deep. For a while, scientists argued about what was making the cold blob cold. There were two main ideas, and telling them apart mattered enormously. The first idea was simple weather. Maybe harsh winds and cloudy skies were pulling heat off the surface of that patch, chilling the top layer of water like a cold breeze skimming the top of a hot drink. If that were the cause, the cold blob would be a shallow, surface-level thing, and probably temporary. The second idea was far more serious. Maybe the patch was cold because the great current was delivering less warm water to it. That would be a deep problem, a sign of the conveyor belt itself weakening, and it would run much further down than the surface. So how do you tell the two apart? You go down. If the cold were only caused by weather chilling the surface, then the cold should stay near the top, and the deeper water should be normal. But if the cold reached far down into the depths, weather could not explain it. Only a change in the current could push cold that deep. Scientists gathered every measurement they could find from inside the cold blob, including readings taken far below the surface. They looked at the water far below the surface, hundreds and then thousands of feet down, and what they found stopped the argument in its tracks. The cold was not sitting on the surface like a thin skin of chill. It plunged deep, reaching down more than 3,000 feet, well over half a mile below the waves. The whole column of water in that region had cooled, top to bottom, far beyond anything a spell of bad weather could ever do. Wind and clouds simply cannot reach half a mile underwater. Something else had chilled that deep water, and the most convincing suspect was a current bringing less heat than it used to. Picture a house in winter. If someone leaves a window open, the room near the window gets chilly, but the rest of the house stays warm. That is weather cooling the surface. But if the whole house goes cold, every room, floor to ceiling, you do not blame an open window. You go check the furnace. The deep cold in the blob was the whole house going cold. It pointed straight at the furnace, the great current, running weak. This was the physical proof scientists had been hunting for. The slowdown had finally become something you could touch and point to. It was a vast pool of chilled water reaching deep into the North Atlantic, exactly where a failing current would leave it, and exactly as deep as a failing current would reach. Once you accept that the current is weakening, a new and urgent question takes over. Why? What could possibly slow down a river more powerful than 100 Amazons, a machine that has run without pause for longer than human history? The answer traces back to the one ingredient the sinking water cannot live without: the salt. And near the top of the world, a melting giant is quietly washing that salt away. Near the top of the world, an island of ice the size of a continent is melting, and every drop of it is fresh water. Remember the secret engine of the whole system. Up near Greenland, cold and salty water grows heavy enough to sink, and that sinking is what drives the entire conveyor belt. The machine runs on heavy water plunging into the deep. Take away the heaviness, and the sinking slows, and the belt loses its power. Two things make that northern water heavy: the cold and the salt. Now watch what happens when you pour in fresh water. Greenland is buried under a sheet of ice more than a mile thick in places, a frozen dome so massive it has its own weather. For thousands of years it stayed roughly in balance, but as the planet has warmed, Greenland has begun to melt at a staggering pace. Every single year, hundreds of billions of tons of ice turn to water and run off into the sea around it. That is a flood of fresh water, with no salt in it at all, pouring straight into the exact region where the ocean needs its water salty and heavy. Here is the problem in one line: fresh water is lighter than salty water. When all that meltwater spills into the North Atlantic, it dilutes the sea, making the surface water fresher and therefore lighter. And lighter water does not want to sink. So the meltwater acts like a lid. It spreads across the top of the ocean near Greenland, a layer of light, fresh water sitting on top, refusing to plunge into the deep the way the heavy, salty water used to. The sinking that powers the whole belt begins to choke. The engine, starved of the heavy water it runs on, starts to slow. Think of it like trying to sink a beach ball versus a bowling ball. The heavy salty water is the bowling ball. It drops straight to the bottom, no problem. Fresh meltwater is the beach ball. Push it under and it pops right back up, stubbornly floating. Replace the bowling balls with beach balls, and your sinking machine simply stops working. This is the terrifying link that ties everything together. A warming planet melts Greenland. Melting Greenland dumps fresh water into the North Atlantic. Fresh water refuses to sink. The sinking drives the current, so a stalling sink means a weakening current. And a weakening current delivers less heat north, which cools that patch of sea into the cold blob we have been chasing this whole time. Every piece connects. It also explains the strangest clue of all, the lopsided pattern that split the scientists earlier. A weakening current leaves the far north oddly cold, right where the heat used to arrive, while heat piles up further south with nowhere to go. Cold north, warm middle. That is not what a friendly cycle looks like. That is what a jamming machine looks like. So the meltwater is the prime suspect. The more Greenland melts, the fresher the north gets, and the more the great current struggles. And that raises the scariest question of all. If the current is already slowing, how would we know if it were approaching a true breakdown? Is there any warning sign, any flashing red light, that would tell us the machine is about to fail? There is, and it has already started blinking, just off the American coast. Just off the coast of North Carolina, the mightiest current in the Atlantic has started drifting out of place. The warning sign is hiding in the Gulf Stream, the warm, fast part of the current that races up the eastern edge of the United States. For as long as anyone has measured it, the Gulf Stream has followed a familiar path, hugging the coast and then swinging out to sea near a spot called Cape Hatteras, a hook of land jutting off North Carolina. Sailors and scientists have tracked its position there for generations. It was one of the steady, dependable features of the ocean. Lately, though, it has been creeping. When scientists lined up decades of measurements, using satellites that read the height and temperature of the sea surface from space, they spotted a clear trend. The Gulf Stream near Cape Hatteras has been slowly shifting northward, drifting away from its old, familiar track. They double-checked it against older records reaching back more than half a century, taken by instruments down in the water, and those agreed. The current is on the move, edging north year by year. At first that might sound minor, so a current shifted a little. Why should anyone care where a river in the sea decides to flow? The answer is that this particular drift may be an early warning, a symptom that shows up long before the real trouble arrives. Here is why. When scientists build detailed computer models of the ocean and force the great current to weaken inside them, they see something striking happen to the Gulf Stream. As the current loses strength, the Gulf Stream begins to slide northward near Cape Hatteras, in exactly the way the real one is sliding now. The model behaviour and the real behaviour match. So the drift we are watching off North Carolina looks like the signature of a weakening current, written on the map for anyone to read. Think of it like the first faint symptom of an illness. A cough on its own is nothing. But if doctors know that a certain dangerous disease always begins with that exact cough, they stop ignoring it. The northward creep of the Gulf Stream is that kind of cough. Small on its own, but meaningful because of what usually follows it. And what follows it, in the models, is the part that made scientists sit up straight. In the simulations, the slow northward drift is only the opening act. It goes on gently for a while, the current easing north a little at a time, year after year, just as we see today. Then, at a certain point, the models show the Gulf Stream do something violent. It stops creeping and lunges, jumping a huge distance north in a shockingly short time. A slow drift turns into a sudden leap. That leap in the models is a marker. It shows up decades before the great current would fully collapse, like a loud alarm bell ringing well ahead of the disaster, giving a warning that the machine is heading toward a breakdown. So the quiet drift we see today may be the calm before a lurch. The question every scientist wants answered is simple and chilling. How big is that leap, and how fast does it come? The models gave an answer, and it was faster than almost anyone expected. In the computer models, the current does not fail slowly and gently. At one moment, it jumps. Scientists built a highly detailed simulation of the Atlantic, a digital copy of the ocean precise enough to capture the swirls and paths of the real currents. Then they did something they could never do to the real world. They slowly poured extra fresh water into the model's North Atlantic, mimicking the meltwater flooding off Greenland, and they watched to see how the great current would respond as it was pushed toward a breakdown. For a long stretch, the model behaved calmly. The current weakened bit by bit, and the Gulf Stream drifted north slowly, easing away from its usual track a little at a time. It was the same gentle creep we see in the real ocean today. Nothing sudden, nothing alarming, just a slow, patient decline that might lull you into thinking there was plenty of time. Then the model hit a moment, and everything changed at once. The Gulf Stream, which had been drifting north gently for ages, suddenly lurched. In the space of just 2 years, it leapt roughly 140 miles to the north, a violent jump after all that slow creeping. 2 years, that is barely longer than the time between one presidential election and the next. A feature of the ocean that had held its position for all of human history shoved 140 miles in the blink of an eye. That distance is hard to picture, so anchor it. 140 miles is about the length of a long day's drive, or the span of a small state end to end. Imagine the entire warm river offshore picking itself up and slamming that far up the coast in the time it takes a kid to finish middle school. In ocean terms, that is an explosion in slow motion. And here is the detail that turns the jump from fascinating into frightening. In the model, that sudden leap happened decades before the current actually collapsed. It was an early warning, a red flag raised long before the real catastrophe. The lurch is the ocean's way of announcing that it has crossed onto a dangerous path, with the true breakdown still some years down the road. That should sharpen your attention on what is happening right now off North Carolina. Today, the real Gulf Stream is doing the slow, gentle creep. The calm part of the story, the part before the lurch. Nobody can say for certain whether the real ocean will ever take the violent leap the model took. A simulation is a careful guess about reality, built by smart people, but still a guess. The real ocean may prove more stubborn or more fragile than any model predicts. But the match between the model and the real world, at least in this early, gentle stage, is enough to make scientists deeply uneasy. We appear to be living through the quiet opening act that the simulation warned about. Whether the loud second act ever arrives is one of the biggest open questions in all of climate science. If the current truly did lurch and then weaken toward collapse, the effects would come home to America fast, and one of the very first would rise right along the East Coast. It would not arrive as a distant abstract worry. It would arrive as water in the streets. Because a weakening current does something surprising and direct to the sea itself. It piles the ocean up against the American shore. When the great current weakens, the ocean does something you would never guess. It leans toward America and rises. This is one of the strangest and most important effects of a slowing current, and it takes a moment to wrap your head around. A fast-moving current like the Gulf Stream actually pulls water away from the coast as it races along. The speed and the spin of the planet work together to hold a kind of slope in the sea surface, keeping the water offshore piled a little higher and the water near the coast pulled a little lower. As long as the current runs fast, that slope holds, and the coast sits at its normal level. Now slow the current down. When the current weakens, it stops pulling the water offshore as strongly. The slope in the sea surface relaxes, and all that water that was being held out to sea comes sliding back toward the shore. It sloshes up against the coast and raises the sea level right where people live. So a weakening current, far out in the middle of the ocean, ends up dumping extra water directly onto the American coastline. It is a spooky, invisible connection. Change you cannot see, happening hundreds of miles offshore, quietly lifts the water in the harbour at your feet. And this effect does not hit the whole world evenly. It lands hardest on one particular stretch of coast. The northeastern United States, the shoreline running from roughly Virginia up through New York and New England, is exactly the region where a weakening Gulf Stream piles the most extra water. The very coast with the biggest, most crowded cities is the coast most exposed to this hidden surge. Scientists have already watched this play out. Along parts of the northeastern coast, the sea has been rising faster than the global average, and studies tie some of that extra rise to the changing current offshore. When the current has had brief slowdowns in the past, the northeastern coast has seen quick jumps in sea level, a foot of water arriving in a season or two far faster than the slow global creep. The ocean responded to the stalling current almost immediately. Picture a bathtub with someone holding a board upright in the middle, pressing the water toward one end so it piles higher there. That tilt is the fast current holding water offshore. Now let go of the board. The piled water rushes back and the level rises at the near end of the tub. That near end is the American Northeast. Let the current relax and the water comes home to roost against those shores. Stack this on top of the sea level rise the whole world is already facing from melting ice and warming seas, and the Northeast faces a double blow. The global rise lifts every coast slowly. The weakening current adds an extra local surge on top, aimed straight at some of the most valuable real estate in the country. That is the abstract version, water and slopes and averages. But the real meaning of it shows up somewhere far more personal. It shows up in specific cities, in specific streets, in the basements and subways and front doors of places where millions of Americans live and work. To feel what this really means, you have to walk those streets as the water starts to climb. Imagine the morning tide rolling into a coastal city on a clear sunny day, with no storm anywhere in sight, and still the streets go under. That is already happening in parts of the United States, and a weakening current threatens to make it far worse. There is a name for it now, coined by the people who live with it. Sunny day flooding. It is water that creeps up through storm drains and over seawalls at high tide, flooding streets and parking lots on days with blue skies and not a drop of rain. The ocean simply rises high enough to spill into the city on its own. Consider the region around Norfolk in Virginia, one of the places on the American coast most exposed to rising seas. It sits low and flat, right where a weakening current piles up extra water, and it is also home to a massive naval base, a cornerstone of the country's defence. The land there is slowly sinking even as the sea climbs, a double squeeze. Residents already plan their days around the water, rerouting around streets that vanish under the sea a few times a month. Now move up the coast to New York City. Picture the subway, that vast underground web of tunnels that carries millions of people every single day, threaded beneath streets that sit barely above the waterline. A higher sea means every storm pushes water further inland and deeper into those tunnels. The city already got a brutal preview years ago when a single great storm flooded the subways and knocked out power to whole neighbourhoods. A permanently higher sea would turn that kind of nightmare from a rare disaster into a regular threat. Then there is Boston, with its historic downtown built on low, filled inland right at the water's edge, and dozens of other towns and cities up and down the northeastern coast, each with its own low streets and its own vulnerable edge where the land meets the sea. All of them sit in the exact zone where a slowing current would raise the water the most. Here is what makes this so much scarier than slow, ordinary sea level rise. The rise from the weakening current could come in fast bursts, not a gentle creep you have decades to prepare for. If the current lurches, as the models warn it might, the northeastern coast could see the sea jump up in just a few years. Cities that thought they had until the end of the century to build defences might find the water arriving in a single decade. That speed is the real danger. People and cities can adapt to a threat that arrives slowly. You can build sea walls, raise buildings, redesign drains, and move over time. But a sudden surge, water climbing faster than anyone planned for, overwhelms the defences before they are ready. The difference between slow and fast is the difference between a manageable challenge and a disaster. So the fate of these great American cities, home to tens of millions of people and a huge share of the country's wealth, is tied to the health of a current far out at sea. A machine most of those residents have never heard of could decide whether their streets stay dry. All of this raises the question that sits at the very heart of the fear. Is the current simply slowing down in a way that might level off? Or is it sliding toward a cliff, a point where it tips over and cannot climb back? The scariest word in this entire story is not collapse. It is a quieter one, tipping. Everything we have talked about so far, the slowing current, the cold blob, the drifting Gulf Stream, describes a machine losing strength gradually. A slow decline is frightening enough. But scientists fear the great current may have a far nastier trick hidden inside it. They fear it may be what they call a tipping element, a system that can pass a hidden line and then flip suddenly and permanently into a completely different state. Here is what a tipping point really means. Most changes are reversible. If you warm something up, you can cool it back down. If a current slows, you might hope that fixing the cause would let it speed back up. A tipping point breaks that comforting logic. Past a certain threshold, the change locks in and feeds on itself, and even if you undo what caused it, the system will not return to how it was. Picture leaning back in a chair, balancing on the two rear legs. For a while you can lean further and further and still catch yourself, and rock back to safety. The chair is tilting, but it is recoverable. Then you cross one invisible angle just 1 degree too far and suddenly gravity takes over. No amount of flailing brings you back. You're going over, and the fall finishes itself. That single degree, the line between catching yourself and crashing, is a tipping point. The great current may have a line just like that, and the reason is buried in the very engine we already explored, the sinking of heavy water near Greenland. That sinking can feed on itself in a dangerous way. When the current weakens, it carries less salty water north, which makes the northern water fresher and lighter, which makes it sink even less, which weakens the current even more. Round and round the loop goes, each turn making the next one worse. A slowing current can drive its own further slowing until it spirals down and shuts off. Once that spiral takes hold and the current tips into a collapsed state, It could stay collapsed for a very long time, perhaps centuries, no matter how much we later try to fix things. That is the horror of a tipping point. There is no undo button on the other side of the line. And here is the part that keeps scientists up at night. Nobody knows exactly where the line is. The great current has tipped and collapsed before in Earth's distant past, so we know it can happen. But pinpointing the precise threshold, the exact angle of the chair, is fiendishly hard. We might be far from it. We might be uncomfortably close. We might, in the worst case, have already crossed it without knowing, with the full collapse still working its way toward us. That uncertainty is the whole problem. When you're leaning back in the chair blindfolded, unable to see the tipping angle, every extra degree of lean is a gamble, and humanity keeps leaning further, warming the planet and melting Greenland faster each decade, pushing the current toward a line we cannot see. This is exactly the point where the scientists themselves split into camps and start to argue, loudly. Some look at all of this and sound the alarm as loudly as they can. Others urge everyone to slow down and be careful with such a terrifying claim. That argument, between the alarmed and the cautious, is one worth listening to closely. Put two of the world's top ocean scientists in a room, ask them how scared we should be, and you may start a fight. This is the honest heart of the story. The great current, its slowdown, and the risk of collapse sit right on the frontier of science, where the evidence is real but still incomplete, and where brilliant people look at the same facts and reach different conclusions. There is a genuine split, and understanding it matters more than picking a side. On one side stand the alarmed. These scientists look at the weakening current, the deep cold blob, the drifting Gulf Stream and the melting of Greenland, and they argue that the danger is being taken far too lightly. Their case is that the warning signs are lining up, that the current has clearly lost strength, and that the possible cost of a collapse is so catastrophic that we should treat even a modest chance of it as an emergency. To them, waiting for perfect proof is a reckless gamble, because by the time the proof is undeniable, the tipping point may already be behind us. They want the world to act now, while there is still time to matter. On the other side stand the cautious. These scientists do not deny that the current matters or that the climate is warming. Their worry is about certainty. They point out that measuring a system this vast, with records that are patchy and short compared to the current's slow rhythm, leaves huge room for error. A few of them are not even convinced the long-term slowdown is as clear as the alarmed camp claims. They fear that crying collapse too loudly, before the science is solid, could backfire, spreading panic or making people tune out real climate concerns. They urge patience, more measurements, and careful language. Both camps are staring at the same ocean. Both are full of serious, honest experts. They simply weigh the evidence and the risks differently, and each side has a point worth respecting. The alarmed camp may well be right that we are closer to danger than we think. The cautious camp may be right that the exact risk is still fuzzy, and both of those things can be true at once. The situation can be genuinely uncertain and genuinely dangerous at the same time, the way a lump can be uncertain and still worth rushing to the doctor about. What almost nobody in the field argues is that we should simply ignore it. Even the most cautious scientists agree the current is worth watching closely because the stakes are so enormous. When the possible downside is the loss of a system that warms half a hemisphere, even a small chance is worth taking seriously. You do not need to be certain your house will burn down to buy a smoke detector. So the debate is really about how loudly to sound the alarm and how fast to act while the picture is still coming into focus. That is a hard, important argument, and it is playing out right now in journals and conferences around the world. To understand why even the cautious scientists take the risk seriously, it helps to know one more thing. The Earth has run this experiment before, all on its own, long ago. And the record of what happened is frozen into the ice and buried in the mud at the bottom of the sea. The last time this current collapsed, the world had no factories, no cars, and no idea what hit it. The great conveyor belt has broken down before, long before humans were around to measure it. We know this because the Earth keeps its own records, and scientists have learned how to read them. Deep in the ice of Greenland and in the mud, at the bottom of the ocean, the planet has stored a diary of its ancient climate, and that diary tells the story of a current that once shut off. Start with the ice. Every year snow falls on Greenland and packs down into a fresh layer of ice, trapping tiny bubbles of ancient air and chemical clues about the temperature that year. Drill straight down through the ice sheet, and you drill back through time, one layer for each year, going back tens of thousands of years. Scientists have pulled up cores of this ice, long cylinders like frozen tree rings, and read the climate history layer by layer. Then there is the seabed. Down on the ocean floor, mud piles up slowly, year after year, burying the shells of tiny sea creatures. Those shells lock in clues about how warm the water was and how the current was flowing when they were alive. Drill into the seabed and pull up a core of that mud, and you get another diary, this one written on the ocean bottom. Both diaries tell the same dramatic story. Around 12,000 years ago, as the world was warming up out of an ice age, a huge surge of fresh water poured into the North Atlantic from melting ice. Sound familiar? That freshwater flood did exactly what scientists fear could happen again. It choked the sinking, and the great current faltered and largely shut down. The result was brutal and fast. With the current no longer hauling heat north, the whole North Atlantic region plunged back into bitter cold, almost like being yanked back into the Ice Age for a while. The ice cores show temperatures in the region dropping sharply, and the change did not take centuries to arrive. In some records, a big share of the cooling slammed down within a single human lifetime, and parts of it may have snapped into place in just a decade or two. Let that comparison settle into the picture. A warming world, a flood of fresh water into the North Atlantic, a current that stalls, and then a violent swing into cold across an entire region, arriving fast enough that a person could watch their whole world change. That is the historical precedent. That is the experiment the Earth has already run, written into ice and mud for us to find. The world is a very different place now, far warmer overall, so a modern collapse would play out differently than the ancient one. It would not simply drop us into an ice age, but the ancient record proves the core fear is real. This current genuinely can shut down. It has done so before, and when it did, the climate lurched hard and fast, not gently. Knowing that it can happen, and seeing the warning signs today, some scientists have started asking a wild question. If the current really is heading for a cliff, is there anything at all that human beings could do to save it? The answer people are seriously discussing sounds like something out of science fiction. To rescue the ocean's greatest current, some scientists have floated an idea so enormous it sounds insane. Build a dam between two continents. As the danger to the great current has grown clearer, a handful of researchers have started asking a desperate question. If warming and melting keep pushing the current toward collapse, could we engineer our way out of it? Could humanity physically step in and keep the machine running? The proposals that come back are staggering in scale, the kind of thing that stretches the limits of what people could ever actually build. The boldest one involves a narrow gap at the top of the world. Way up north, between the far eastern tip of Russia and the western edge of Alaska, there is a stretch of sea called the Bering Strait. It is the doorway between the Pacific Ocean and the Arctic, and it is surprisingly narrow, only about 50 miles across. 50 miles of open water separating two continents. The idea is to build a dam straight across it, a wall spanning that entire 50-mile gap from Alaska to Russia, plugging the doorway between the two oceans. Why on earth would that help the Atlantic half a world away? The thinking goes like this. A dam across the Bering Strait could block fresh, cold water from flowing out of the Arctic and into the North Atlantic. Since it is exactly that kind of fresh water that threatens to choke the sinking and stall the current, keeping some of it out might help protect the salty heaviness the current needs to keep turning. In theory, sealing off one doorway might steady the whole global system. Take a moment to picture the sheer size of this. A solid barrier 50 miles long, anchored in one of the coldest, stormiest, most remote seas on the planet, where winter brings crushing ice and months of darkness. It would be one of the largest structures ever built by human hands, raised in one of the most hostile places imaginable. The cost would be almost beyond counting, and the effort would require nations that often distrust each other to join together for a project lasting generations. And nobody is sure it would even work. Tinkering with something as vast as the global ocean is wildly risky. Block one current, and you might trigger unexpected changes somewhere else, solving one problem while creating 3 new ones. The ocean is a deeply connected system, and yanking on one part of it can send ripples in directions no one predicted. Most scientists treat ideas like the dam as a last-ditch measure, a sign of how desperate the situation could become, rather than a plan anyone truly wants to attempt. The very fact that serious people are sketching out 50-mile dams between continents tells you how seriously they take the threat. You do not dream up engineering projects of that scale for an imaginary problem. The dam idea is a mirror. It reflects just how frightening the possible loss of this current really is, and how few good options we would have if it began to fail in earnest. But here is a bitter twist that makes the whole situation harder. Even as the danger grows and the stakes climb, our ability to watch the current, to keep our eyes on the machine and catch trouble early, may be about to get weaker instead of stronger. We could be walking toward the edge of a cliff and choosing that exact moment to turn off the flashlight. To catch a disaster before it strikes, you have to be watching. And right now, our watchers in the ocean are under threat. Everything we have learned about the great current, its slowdown, its warning signs, its deep cold, comes from one thing: measurement. Instruments placed in the water, patiently recording the ocean day and night for years on end. Lines of sensors strung across the Atlantic, floating robots drifting through the depths, buoys bobbing on the surface. These are our eyes on the machine. Without them, we would be blind, guessing at the health of a system that could reshape the planet. These instruments are the only reason scientists spotted the trouble at all. The cold blob, the deep chill, the drifting Gulf Stream, the slowdown itself, none of it would be known without the steady stream of data pouring in from the sea. Keeping those instruments running, and adding more of them, is how we would catch a real collapse in its early stages, while there might still be time to react. Here is the troubling part. Keeping a vast array of ocean instruments running is expensive and difficult. The machines drift, break, run out of power, and get battered by storms. They have to be maintained, replaced, and paid for year after year by governments and research programs that are always fighting over limited budgets. Ocean monitoring is easy to cut because the harm from cutting it does not show up right away. The instruments simply go quiet and the danger builds unseen. And cuts are exactly what looms. There are plans on the table that would pull large numbers of monitoring instruments out of the water, including sensors that help keep watch on the very current we have been discussing. Hundreds of these deep-sea devices could be removed, thinning out the network of eyes just as the thing they watch grows more unstable. The timing could hardly be worse. Think about how backward that is. Picture a patient in a hospital bed, hooked to monitors tracking a heart that doctors already suspect is failing. Now picture someone walking in and unplugging the monitors to save money. The heart is no healthier for being unwatched. The only thing that changes is that when the crisis comes, nobody sees it in time to help. Turning off the monitors does not remove the danger. It just removes the warning. That is the risk we are flirting with in the ocean. The great current may or may not be sliding toward a tipping point. But our best hope of knowing, of catching the lurch early, and buying ourselves time to respond, depends entirely on keeping our instruments in the water and our eyes open. Pull the sensors, and we lose our early warning at the worst possible moment. It is a strange kind of danger, this one. A slow blinding, a quiet choice to look away from the one part of the planet we most need to watch. The current could weaken in the dark, and we might only learn how far it had gone once the effects washed up on our shores. So we arrive at the end of the journey with a single, enormous question hanging over everything. We have followed the cold water from the surface down into the deep, from a friendly cycle to a failing machine, from calm hurricane seasons to flooded cities and frozen possibilities. Now it all comes down to which Atlantic we are truly looking at. Everything we have chased across this whole journey comes down to one cold patch of water and two very different futures. Go all the way back to the beginning, to that stubborn blue blob on the map south of Greenland. We have seen that it can tell two completely different stories, and the fate of America hangs on which one is true. In the first story, the cold blob is the friendly face of nature. It is the leading edge of the Atlantic's slow, natural cycle, swinging from its warm mood into a cool one, the same rhythm the ocean has followed for thousands of years. If that is the real story, then America is in for a mixed but manageable future. Calmer hurricane seasons along the coast, more rain for the farms in the heartland, a break however temporary from the relentless heat, a cooler Atlantic that hands the country a decade or two of relief, before the wave swings back toward warm again, as it always has. In the second story, that same cold blob is a warning. It is the fingerprint of a mighty ocean current beginning to fail, the central heating system of the North Atlantic winding down. If that is the real story, then America faces something far darker, seas surging faster against the crowded northeastern coast, sunny day floods creeping into cities like New York, Boston and Norfolk, weather patterns thrown into chaos as the planet's heat delivery system stutters. And behind it all, the shadow of a tipping point, a line that once crossed cannot be uncrossed for centuries. Same patch of water, two futures, one gentle, one severe. And the maddening truth is that scientists cannot yet say for certain which one we are living in. The clues point in both directions. The cold is real. The slowdown looks real. The lopsided pattern hints at the darker story. But the ocean is vast and slow and stubborn, and it guards its secrets closely. Here is what makes this more than just a fascinating puzzle. It is your future sitting on that scale. If you are young, the answer to this question will shape the world you grow into, the storms you live through, the cost of the food you eat and the home you insure, whether the great coastal cities of America stay dry or fight a rising sea. All of it rides on the behaviour of a river hidden in the deep, a machine most people have never even heard of until now. The most honest thing anyone can tell you is that the story is still being written, right now, in the cold water off Greenland and in the drifting current off the Carolina coast. Scientists are watching as closely as they can, arguing, measuring and racing to understand the machine before it makes its choice for us. Every new reading is another clue. Every year brings the answer a little closer into focus. So the next time you hear someone mention the Atlantic, picture a living, breathing, moving giant, with a heartbeat that takes decades and a hidden engine that warms half the world. And right now, that giant is doing something it has not done in a very long time. It is changing. The only question left is how far it will go, and whether we will be watching closely enough to see it happen.